Okay, so last time we looked at and played this game. You had to choose grades, you had to choose alpha and beta, and this table told us what outcome would arise. In particular, what grade you would get and what grade your pair would get. So for example, if you'd chosen beta and your pair had chosen alpha, then you would get a C and your pair would get an A. And one of the first things we pointed out is that this is not quite a game yet. It's missing something. This has outcomes in it. It's an outcome matrix. But it isn't a game because for a game, we need to know payoffs. Okay? And then we looked at some possible payoffs, and now it is a game. So this is a game, just to give you some more jargon, this is a normal form game. And here we've assumed the payoffs are those that arise if players only care about their own grades, which I think was true for a lot of you. It wasn't true for the gentleman who's sitting there now, but it was true for a lot of people. All right? And we pointed out that in this game, alpha strictly dominates beta. What do we mean by that? We mean that if these are your payoffs, no matter what your pair does, you attain a higher payoff from choosing alpha than you do from choosing beta. Right? Let's focus a couple of lessons of the class before I come back to this. One lesson was, do not play a strictly dominated strategy. Ever remember that lesson? And then much later on, when we looked at some more complicated payoffs and a more complicated game, we looked at a different lesson, which was this. Put yourself in others' shoes to try and figure out what they're going to do. Right? So in fact, what we learn from that is it doesn't just matter what your payoffs are, that's obviously important, it's also important what other people's payoffs are, because you want to try and figure out what they're going to do and then respond appropriately. Right? So we're going to return to both of these lessons today. Right? Both these lessons will reoccur today. Now, a lot of today is going to be fairly abstract, so I just want to remind you that game theory has some real-world relevance. And again, still in the interest of recapping, this particular game is called the prisoner's dilemma. It's written there, the prisoner's dilemma. All right, notice it's prisoners plural. And we mentioned some examples last time. Let me just reiterate and mention some more examples which are actually written here so they'll find their way into your notes. So for example, if you have a joint project that you're working on, perhaps it's a homework assignment, or perhaps it's a video project like these guys, that can turn into a prisoner's dilemma. Why? Because each individual might have an incentive to shirk. All right? Price competition. Two firms competing with one another in prices can have a prisoner's dilemma aspect about it. Why? Because no matter how the other firm, your competitor, prices, you might have an incentive to undercut them. If both firms behave that way, prices will get driven down towards marginal cost and industry profits will suffer. In the first case, if everyone shirks, you end up with a bad product. In the second case, if both firms undercut each other, you end up with low prices that's actually good for consumers, but bad for firms. And let me mention a third example. Suppose there's a common resource out there. Maybe it's a fish stock, or maybe it's the atmosphere. Right? There's a prisoner's dilemma aspect to this too. You might have an incentive to overfish. Why? Because if the other countries with this fish stock, let's say the fish stock is the Atlantic, if the other countries are going to fish as normal, you may as well fish as normal too. And if the other countries aren't going to cut down on their fishing, then you want to catch the fish now because there aren't going to be any there tomorrow. Right? Another example of this would be global warming and carbon emissions. Again, leaving aside the science, about which I'm sure some of you know more than me here, the issue of carbon emissions is a prisoner's dilemma. Each of us individually has an incentive to emit carbons as usual. Right? If everyone else is cutting down, I don't have to. And if everyone else does cut down, I don't have to. I end up using hot water and driving a big car and so on. Right? In each of these cases, we end up with a bad outcome. So this is socially important. This is not just some abstract thing going on in the class in Yale. And we need to think about solutions to this right from the start of the class. And we already talked about something. We pointed out that this is not just a failure of communication. All right? Communication per se will not get you out of a prisoner's dilemma. You can talk about it as much as you like, but as long as you're going to go home and still drive your Hummer and have 16 hot showers a day, we're still going to have high carbon emissions. You can talk about working hard on your joint problem set, right? But as long as you go home and don't work hard, it doesn't help. All right? In fact, if the other person is working hard or is cutting back on their carbon emissions, you have every bit more incentive to not work hard or keep high carbon emissions yourself. So we need something more, and kind of things we can see more. We can think about contracts. We can think about treaties between countries. We can think about regulation. All of these things work by changing the payoffs. Not just talking about it, but actually changing the outcomes, and changing the payoffs. Right? Changing the incentives. Right? Another thing we can do, very important thing, is we can think about changing the game into a game of repeated interaction and seeing how much that helps. And we'll come back and revisit that later in the class. And one last thing we could think of doing, but we have to be a bit careful here, is we could think about changing the payoffs by education. Right? I think of that as the Maoist strategy. Right? Lock people up in classrooms and tell them they should be better people. That may or may not work. I'm not optimistic, but at least it's the same idea. We're changing payoffs. All right? So that's enough for recap. And I want to move on now. And in particular, we left you hanging at the end last time. We played a game at the very end last time where each of you chose a number. All right? All of you chose a number. And we said the winner was going to be the person who gets closest to 2/3 of the average in the class. Now, we figured that out. We figured out who the winner is. And I know a lot of you are trying to see if you won. Is that right? And I'm going to leave you in suspense. Okay, so I'm going to tell you today who won. We did figure it out. And we'll get there. But I want to do a little bit of work first. All right? So I'm just going to leave it in suspense. That'll stop you walking out early if you want to win the prize. All right. So there's going to be lots of times in this class when we get to play games, we get to have classroom discussions, and so on. But there's going to be some times when we have to slow down and do some work. And the next 20 minutes are going to be that. All right? So with apologies for being a bit more boring for 20 minutes, let's do something we'll call formal stuff. Right? In particular, I want to develop and make sure we all understand what are the ingredients of a game. All right? So in particular, we need to figure out what formally makes something into a game. And the formal parts of a game are this. We need players. All right? And while we're here, let's develop some notation. So for standard notation for players, I'm going to use things like little I and little j. All right? So in that numbers game, the game when all of you wrote down a number and handed it in at the end of last time, the players were who? Players were you, right? You all were the players. Right? A useful text and expression meaning you plural. Right? In the numbers game, we'll give us a bit more room here. In the numbers game, you all were the players. All right? Second ingredient of the game are strategies. There's a good clue here. If I'm writing, you should be writing. Okay? Strategies. All right? Notation. All right? So I'm going to use little si, to be a particular strategy of player I. Particular strategy of player I. So an example in that game might have been choosing the number 13. All right, everyone understand that? Now I need to distinguish this from the set of possible strategies of player I. So I'm going to use capital SI to be what? To be the set of alternatives, the set of possible strategies of player I. So in that game we played at the end last time, what were the set of strategies? They were the set 1, 2, 3, all the way up to 100. All right, so I'm distinguishing a particular strategy from the set of possible strategies. And while we're here, I want a third notation for strategy. I'm going to use little s without an I, all right, no subscripts, little s without an I, to mean a particular play of the game. A particular play of the game. So what do I mean by that? All of you at the end last time wrote down this number and handed them in. So we had one number, one strategy choice for each player each person in the class. So here they are. Here's my collected in set of strategy choices. Here's the bundle of bits of paper you handed in last time. This is a particular play of the game. All right, I've got each person's name, and I've got a number from each person, a strategy from each person. All right, we actually have it on a spreadsheet as well, so here it is written out on a spreadsheet. Right? Each of your name is on this spreadsheet, and the number you chose. All right, so that's a particular play of the game, and that has a different name. We sometimes call this a strategy profile. So in the textbook, you'll sometimes see the term a strategy profile or a strategy vector or a strategy list. It doesn't really matter. What it's saying is one strategy for each player in the game. All right? So in the numbers game, this is the spreadsheet. Or an example of this is the spreadsheet. All right? I need to make it so you can still see that. I'm going to pull down these boards. And let me clean something. So you might think we're done, right? We've got players. We've got the choices they could make. That's their strategy sets. We've got those individual strategies. And we've got the choices they actually did make. That's the strategy profile. Seems like we've got everything you could possibly want to describe a game. What are we missing here? Shout it out. Payoffs. We're missing payoffs, right? So to complete the game, we need payoffs. All right? And again, I need notation for payoffs. So in this course, I'll try and use U for utile to be player I's payoff. All right? So UI will depend on player 1's choice all the way to player I's own choice, all the way up to player N's choices. All right? So player I's payoff, UI, depends on all the choices in the class, in this case, including her own choice. And of course, a shorter way of writing that would be UI S. It depends on the profile. All right? So in the numbers game, what is this? In the numbers game, UI of S can be two things. It can be $5 minus your error in pennies if you won. I guess it could be something if it was a tie. I won't bother writing that now. And it's going to be 0 otherwise. All right? So we've now got all of the ingredients of the game. Players, strategies, payoffs. All right? Now we're going to make an assumption today and for the next 10 weeks or so. All right? So for almost all the class. We're going to assume that these are known. We're going to assume that everybody knows the possible strategies everyone else could choose, and everyone knows everyone else's payoffs. Now that's not a very realistic assumption, and we are going to come back and challenge it at the end of the semester, but this will be complicated enough to get us a lot of material in the next 10 weeks. I need one more piece of notation, and then we can get back to having some fun. So one more piece of notation. I'm going to write S minus I to mean what? It's going to mean a strategy choice for everybody except person I. It's going to be useful to have that notation around. All right? So this is a choice for all except person I or player I. So in particular, if you're person 1, then S minus I would be S2, S3, S4 up to Sn, but it wouldn't include S1. All right? And it's useful. Why? Because sometimes it's useful to think about the payoffs as coming from I's own choice and everyone else's choices. It's just a useful way of thinking about things. All right? Now, at this point, I want to stop for a second. And I know that some of you, from past experience, are somewhat math-phobic. You do not have to wave your hands in the air if you're math-phobic. But since some of you are, let me just get you all to take a deep breath. This goes for people who are math-phobic at home too. All right? So everyone's like a slight panic now. You know, you came here today, you thought everything was going to be fine, now I'm putting math on the board. All right? Take a deep breath. It's not that hard. And in particular, notice that all I'm doing here is writing down notation. There's actually no math going on here at all. I'm just developing notation. Now, I don't want anybody to quit this class because they're worried about math or math notation. So if you are in that category of somebody who might quit it because of that, come and talk to me, come and talk to the A's, we will get you through it. All right? It's fine to be math-phobic. I'm phobic of all sorts of things. All right? Not necessarily math, but all sorts of things. All right? So serious thing. A lot of people get put off by notation. It looks scarier than it is. There's nothing going on here except for notation at this point. All right. So let's have an example to help us fix some ideas. And again, I'll have to clean the board, so give me a second. I think an example might help those people who are disturbed by the notation. So here's a game which we're going to discuss briefly. It involves two players, and we'll call the players 1 and 2, and player 1 has two choices, top and bottom, and player 2 has three choices, left, center, and right. Right? It's just a very simple abstract example for now. And let's suppose the payoffs are like this. They're not particularly interesting. We're just going to do it for the purpose of illustration. So here are the payoffs. 5 minus 1, 11, 3, 0, 0. 6, 4, 0, 2, 2, 0. All right, let's just map the notation we just developed into this game. Okay, so first of all, who are the players here? Right, well, there's no secret there. The players are, let's write it down, why don't we? The players here in this game are player 1 and player 2. All right, what about the strategy sets? What about the strategy sets, or the strategy alternatives? All right, so here, player 1's strategy set, she has two choices, top or bottom, represented by the rows, which are helpfully the top row and the bottom row. All right, and player 2 has three choices. Right, this game is not symmetric, so they have different numbers of choices. That's fine. Player 2 has three choices, left, center, and right, represented by the left, center, and right column in the matrix. And just to point out in passing, up to now we've been looking mostly at symmetric games. Notice this game is not symmetric in the payoffs or in the strategies. There's no particular reason why games have to be symmetric. And payoffs, all right, so again, this is not rocket science, but let's do it anyway. So just an example of payoffs. So player 1's payoff, if she chooses top and player 2 chooses center, we read by looking at the top row and the center column, and player 1's payoff is the first of these payoffs, so it's 11. All right? And player 2's payoff, from the same choices, top for player 1, center for player 2, again, we go along the top row and the center column, but this time we choose player 2's payoff, which is the second payoff, so it's 3. Okay? All right, so again, I'm hoping this is calming down the math phobics in the room. Now, how do we think this game's going to be played? This is not a particularly interesting game, but while we're here, why don't we just discuss it for a second? All right, so if our mic guys get a little bit ready here. All right, so how do we think this game should be played? Well, let's ask somebody at random, perhaps. So, Ali, do you want to ask this guy in the blue shirt here? Right? Does player 1 here, does player 1 have a dominated strategy?
No, player 1 doesn't have a dominated strategy. For instance, if player 2 picks left, then player 1 wants to pick bottom, but if player 2 picks center, player 1 wants to pick center.
Good, excellent, very good. I should have got you to stand up, I forgot that, never mind, but that was very clear, thank you. Was that loud enough so people can hear it? Did people hear that? People at the back, do you hear it? So even that wasn't loud enough, okay? So we really need to get people to, that was very clear, very nice. We need people to stand up and shout, otherwise people at the back can't hear. So what, your name is? Patrick. What Patrick said was, no, player 1 does not have a dominated strategy. Top is better than bottom against left, because, bottom is better than top against left because 6 is bigger than 5. But top is better than bottom against center because 11 is bigger than 0. Everyone see that? Right? So it's not the case that top always beats, it's not the case that top always does better than bottom, or that bottom always does better than top. Okay, what about, raise hands this time, what about player 2? Does player 2 have a dominated strategy? Everyone's keeping their hands firmly down so as not to get spotted here. Should we try, Ali, can we try this guy in white? Do you want to stand up and wait till Ali gets there? And really, but yell it out now. Louder.
I believe right is a dominated strategy because if player 1 chooses top, then player 2 will choose center. And I'm getting confused now. It looks better on my paper. But yeah, right is never the best choice.
Okay, good. So let's be a little bit careful here. So your name is? Thomas. So Thomas said something which was true, but it doesn't quite match with the definition of a dominated strategy. What Thomas said was, right is never a best choice. That's true. All right? But to be a dominated strategy, we need something else. We need that there's another strategy of player 2 that always does better. Right? Now that turns out also to be true in this game, but it's a C. All right? So in this particular game, I claim that center dominates right. That center dominates right. So to see that, if player 1 shows top, center yields 3, right yields 0, 3 is bigger than 0. And if player 1 chooses bottom, then center yields 2, right yields 0, 2 is bigger than 0 again. So in this game, center strictly dominates right. All right? What you said was true, but I wanted something specifically about domination here. All right? So what we know here, we know that player 2 should not choose right. All right? Now, in fact, that's as far as we can get with dominance arguments in this particular game. But nevertheless, let's just stick with it a second. I gave you the definition of strict dominance last time, and it's also on the handout, by the way, the handout on the web. But let me write that definition again, using or making use of the notation from the class. So definition, all right, so player I's strategy S little I prime is strictly dominated by player I's strategy SI if, and now we can use our notation, if UI from choosing SI when other people choose S minus I is strictly bigger than UI SI prime when other people choose S minus I. And the key part of the definition is for all S minus I. All right, just say it in words. Player I's strategy SI prime is strictly dominated by her strategy SI if SI always does strictly better, always yields a higher payoff for player I, no matter what the other people do. Right, so this is the same definition we saw last time, just being a little bit more nerdy and putting it in some notation. Okay? Are people panicking about that? People look like deer in the headlamps yet? No, you look all right. Well, all right-ish. All right. Let's have a look at another example. People okay? I can move this? All right. So let's have a slightly more exciting example now. So imagine the following example. An invader is thinking about invading a country. And there are two ways, there are two passes, if you like, through which he can lead his army. And you are the defender of this country, and you have to decide which of these passes, or which of these routes into the country, you're going to choose to defend. And the catch is, you can only defend one of these two routes. All right? So if you want a real-world example of this, think about the 3rd century BC. Someone can correct me afterwards. I think it's the 3rd century BC, when Hannibal is thinking of crossing the Alps. Right? Not Hannibal Lecter, Hannibal the general in the 3rd century BC. The one with the elephants. All right? Okay, so the key here is going to be that there are two passes. One of these passes is a hard pass, it goes over the Alps, and the other one is an easy pass, it goes along the coast. All right? If the invader chooses the hard pass, he will lose 1 battalion of his army simply in getting over the mountains, simply in going through the hard pass. All right? And if he meets your army, whichever pass he chooses, if he meets your army defending a pass, then he'll lose another battalion. All right? Now, I've given you roughly the choices. The choices are going to be for the attacker which pass to choose, and for the defender which pass to defend. But let's put down some payoffs so we can start talking about this. All right? So in this game, the payoffs for this game are going to be as follows. So it's a simple 2-by-2 game. This is going to be the attacker. This is Hannibal. And this is going to be the defender, and I've forgotten which general was defending, and someone's about to tell me, no doubt. And there are two passes you could defend, the easy pass or the hard pass, and there's two you could use to attack through, easy or hard. And again, easy pass here just means no mountains. We're not talking about something on the New Jersey Turnpike. All right? So the payoffs here are as follows, and I'll explain them in a second. All right, so his payoff, the attacker's payoff, is how many battalions does he get to bring into your country? He only has 2 to start with. And for you, it's how many battalions of his get destroyed. So just to give an example, if he goes through the hard pass and you defend the hard pass, he loses 1 of those battalions going over the mountains and the other one because he meets you. So he has none left, and you've managed to destroy 2 of them. Right? Conversely, if he goes on the hard pass and you defend the easy pass, he's going to lose 1 of those battalions, so he'll have 1 left. He lost it in the mountains, but that's the only one he's going to lose because you were defending the wrong pass. All right, everyone understand the payoffs of this game? All right, so now imagine yourself as a Roman general. Right, this is going to be a little bit of a stretch of imagination, but imagine yourself as a Roman general, and let's figure out what you're going to do. You're the defender, what are you going to do? All right, so let's have a show of hands. How many of you think you should defend the easy pass? Raise your hands. Let's raise your hands so you can see them. Keep them up, wave them in the air. Bit of motion, wave them in the air. Should put your flags, okay? Because these are the Romans defending the easy pass. And how many of you think you're going to defend the hard pass? We have a huge number of people who don't want to be Roman generals here. All right, let's try it again. No abstentions, right? I'm not going to penalize you getting the wrong answer. All right, so how many of you think you're going to defend the easy pass? Raise your hands again. And how many think you're going to defend the hard pass? All right, so we have a majority choosing easy pass. Quite a large majority. So what's going on here? Is it the case that defending the easy pass dominates defending the hard pass? Is that the case? Is the case that defending the easy pass dominates defending the hard pass? You can shout out. No, it's not. In fact, we can check that if the attacker attacks through the easy pass, not surprisingly, you do better if you defend the easy pass than the hard pass, 1 versus 0. But if the attacker was to attack through the hard pass, again, not surprisingly, you do better if you defend the hard pass than the easy pass. All right, so that's not an unintuitive finding. It isn't the case that defending easy dominates defending hard. You just want to match with the attacker. Nevertheless, almost all of you chose easy. What's going on? Can someone tell me what's going on? Let's get the mics going a second. So can we catch the guy with the can we catch this guy with the beard? If we just wait for the mic to get there, and if you could stand up, and shout. There you go.
Because you want to minimize the amount of enemy soldiers that reach Rome or whatever the location is.
All right, you want to minimize the number of soldiers that reach Rome. That's true. On the other hand, we've just argued that you don't have a dominant strategy here. It's not the case that easy dominates hard. What else could be going on? While we've got you up, why don't we get the other guy who's got his hand up there in the middle? And again, stand up and shout in that mic. Point your face towards the mic. Good.
It seems as though while you don't have a dominating strategy, it seems like Hannibal is better off attacking through. It seems like he would attack through the easy pass.
Good. Why does it seem that? I guess that's right. We're on the right lines now. Why does it seem like he's going to attack through the easy pass?
Well, if you're not defending the easy pass, he doesn't lose anyone, and if he attacks through the hard pass, he's going to lose at least one battalion.
All right, all right. So let's have a look at it from, let's do the exercise, let's do the second lesson that I emphasized at the beginning. Let's put ourselves in Hannibal's shoes. They're probably boots or something. I don't know, whatever you do when you're riding an elephant, whatever you wear. All right, let's put ourselves in Hannibal's shoes and try and figure out what Hannibal's going to do here. All right, so it could be, from Hannibal's point of view, he doesn't know which pass you're going to defend. All right, but let's have a look at his payoffs. If you were to defend the easy pass, and he goes through the easy pass, he will get into your country with 1 battalion, and that's the same as he would have got if he went through the hard pass. So if you defend the easy pass, from his point of view, it doesn't matter whether he chooses the easy pass, he gets 1 in there, or the hard pass, he gets 1 in there. But if you were to defend the hard pass, if you were to defend the mountains, then, if he chooses the easy pass, he gets both battalions in, and if he chooses the hard pass, he gets no battalions in. All right? So in this case, easy is better. And we have to be a little bit careful. It's not the case that for Hannibal, choosing the easy pass to attack through strictly dominates choosing the hard pass, but it is the case that there's a weak notion of domination here. It is the case, and used to introduce some jargon, it is the case that the easy pass for the attacker weakly dominates the hard pass for the attacker. What do I mean by weakly dominate? It means by choosing the easy pass, he does at least as well, and sometimes better, than he would have done had he chosen the hard pass. All right? So here we have a second definition, a new definition for today. And again, we can use our jargon. Definition: player I's strategy, SI prime, is weakly dominated by her strategy, SI, if, and now we're going to take advantage of our notation, if player I's payoff from choosing SI against S minus I is always as big as or equal to her payoff from choosing SI prime against S minus I, and this has to be true for all things that anyone else could do. And in addition, player I's payoff from choosing SI against S minus I is strictly better than her payoff from choosing SI prime against S minus I for at least one thing that everyone else could do. Right? So just check that exactly corresponds to the easy and hard thing we just had before. Let's say it again. Player I's strategy SI prime is weakly dominated by her strategy SI if she always does at least as well by choosing SI than choosing SI prime, regardless of what everyone else does, and sometimes she does strictly better. All right? And it seems a pretty powerful lesson. Just as we said you should never choose a strictly dominated strategy, you're probably never going to choose a weakly dominated strategy either, but it's a little more subtle. All right? Now that definition, if you're worried about what I've written down here and you want to see it in words, on the handout I've already put on the web that has the summary of the first class, I included this definition in words as well. So compare the definition in words with what's written here in the nerdy notation on the board. All right? Now, since we think that Hannibal, the attacker, is not going to play a weakly dominated strategy. We think that Hannibal is not going to choose the hard pass. He's going to attack on the easy pass. And given that, which should we defend? We should defend easy, which is what most of you chose. So be honest now, was that why most of you chose easy? Yeah, probably was, right? You may be able to read this. All right? So by putting ourselves in Hannibal's shoes, we could figure out that his hard attack strategy was weakly dominated. He's going to choose easy, so we should defend easy. Having said that, of course, Hannibal went through the mountains, which kind of screws up the lesson, but too late now. All right. Now then, I promised you we'd get back to the game from last time. All right. So where have we got to so far on this class? We know from last time that you should not choose a dominated strategy. And we also know we probably aren't going to choose a weakly dominated strategy. And we also know that you should put yourself in other people's shoes and figure out that they're not going to play a strictly or weakly dominated strategy. That seems a pretty good way to predict how other people are going to play. So let's take those ideas and go back to the numbers game from last time. Now before I do that, I don't need the people at home to see this, but how many of you were here last time? How many of you were not? I asked the wrong question. How many of you were not here last time? All right, so we handed out again that game. We handed out again the game with the numbers. But just in case, let me just read out the game you played. This was the game you played. Without showing your neighbor what you're doing, put in the box below a whole number between 1 and 100. We will, and in fact have, calculated the average number chosen in the class, and the winner of this game is the person who gets closest to 2/3 times that average number. They will win $5 minus the difference in pennies. All right, so everybody filled that in last time, and I have their choices here. So let's just, before we reveal who won, let's discuss this a little bit. Let me come down hazardously off this stage and figure out, let's get the mics up a bit a second. We can get some mics ready. All right, so let me find out some people here and see what people did a second. I've got, you can be honest here since I've got everything in front of me. So how many of you chose some number like 32, 33, 34? One hand. Actually, I can tell you, 9 of you did. So shall I read out the names? Will I embarrass people? All right. So we've got Lynette Likusen, we've got Christian Bargen. There's 9 of you here. Let's try it again. How many of you chose numbers between 32 and 34? Yeah. Okay. So a number of you now we're seeing some hands up. All right. So keep your hands up a second. Keep your hands up a second. Those people. All right. So let me ask people why. Can you get your hand into the guy? What's your name? If we get him to stand up a second, and shout out to the class can hear you. What's your name?
Chris.
Chris, you're on this list somewhere. I mean, you're not on this list somewhere. Never mind. What did you choose?
I think I chose 30.
Okay, 30. So that's pretty close. Okay. So why did you choose 30?
Because I thought everyone was going to be around like the 45 range, because 66 is 2/3, or right around of 100, and then we're going to go 2/3 less than that, and I did one less than that one.
All right. Okay. All right. So thank you. Let's get one of the others. There was another one in here. Can you just raise your hands again? The people who are sort of around 33, 34. There's somebody in here. Can we get you to stand up? And you're between mics, so let me. Yep. Go ahead. Shout it out. What's your name, first of all?
Ryan.
Ryan, I must have you here as well. Never mind. What did you choose?
33, I think.
33? Oh, you did. You are Ryan Lowe.
Yeah.
You are Ryan Lowe. Okay. Good. Go ahead.
I thought similar to Chris, actually, and I also thought that if we got 2/3 and everyone was choosing numbers in between 1 and 100, end up 33 would be around the number that would
All
come
right.
out
So just to repeat the argument that we just heard, again, you have to shout it out more than that. I'm guessing people didn't hear that in the room, so just let me repeat it to make sure everyone hears it. A reason for choosing a number like 33 might go as follows. If people in the room choose randomly between 1 and 100, then the average is going to be around 50, say, and 2/3 of 50 is around 33. All right, 33 and a third, literally. All right? So that's a pretty good piece of reasoning. All right? What's wrong with that reasoning? What's wrong with that? What's wrong with that? Can we get the guy, the woman in the striped shirt here? Yeah. Sorry. We haven't had a woman for a while, so let's have a woman. Thank you.
That even if everyone else had the same reasoning as you, it's still going to be way too high.
All right, so in particular, if everyone else had the same reasoning as you, it's going to be way too high, all right? So if everyone else reasons that way, then everyone in the room would choose a number like 33 or 34, and in that case, the average would be what? Sorry, the average, I just told that 2/3 of the average would be what? 22. Something like 22, all right? So the flaw in the argument that Chris and Ryan had, it isn't a bad argument, it's a good starting point, but the flaw in the argument, mistake in the argument, it was the first sentence in the argument. The first sentence in the argument was, if the people in the room choose random, then they will choose around 50. That's true. The problem is, the people in the room aren't going to choose at random. Right? Look around the room a second. Look around yourselves. Do any of you look like a random number generator? Actually, from here I can see some that do. I'm not going to. All right. All right. All right. So I'm actually looking at some of your answers. Maybe some of you are. Right. On the whole, Yale students are not random number generators. They're trying to win the game. All right. So they're unlikely to choose numbers at random. Right. If they We also, a further argument, if in fact everyone thought that way, and if you figured out everyone was going to think that way, then you would expect everyone to choose a number like 33, and in that case, you should choose a number like 22. How many of you, raise your hand a second, how many of you chose numbers in the range 21 through 23? There's way more of you than that. I'll start reading you out as well. There's actually about 12 of you. Raise your hands. There should be 12 hands going up somewhere. There's 2, 3 hands going up, 4, 5 hands going up. There's actually 12 people who chose exactly 22. So considerably more if we include 23 and 21. All right? So those people, I'm guessing, were thinking this way. Is that right? Let me get one of my 22s up again. Here's a 22. Here's a 22. You want to get this guy? So what's your name, sir? Stand up and shout.
Brian.
Yep. And you chose 22?
I chose 22 because I thought that most people would play the game dividing by 2/3 a couple of times and give numbers averaging around the low 30s.
All right. All right. So if you think people are going to play a particular way, in particular if you think people are going to choose the strategy of Ryan and Chris and choose around 33, then 22 seems a great answer. But you underestimate your Yale colleagues. You underestimate your Yale colleagues. In fact, 22 was way too high. Was way too high. All right. Now, again, let's just iterate the point here. Let's just repeat the point here. The point here is when you're playing a game, you want to think about what other people are trying to do to try and predict what they're trying to do. And it's not necessarily a great starting point to assume that the people around you are random number generators. They have aims, trying to win, and they have strategies too. Let me take this back to the board a second. So in particular, are there any strategies here we can really rule out? So we said already people are not random. Are there any choices we can just rule out? We know people are not going to choose those choices. Let's have someone here. We have the guy in green. Just wait for LA. There you go. Good. Stand up. Give me your name.
My name's Nick.
And shout it out so people can hear.
No one is going to choose a number over 50.
No one's going to choose a number over 50. Okay. I was going to. That actually got. Okay. That's fair enough. Some people did. It's fair enough. I was thinking something a little bit less. I mean, that's fine. I was thinking something a little bit less ambitious. Somebody said 66. Somebody said 66. So let's start analyzing this. All right. So in particular, there's something about these strategy choices that are greater than 67 at any rate. All right. Certainly, I mean, certainly 66. Let's go up a little bit. So these numbers bigger than 67. What's wrong with numbers bigger than 67? What's wrong? Raise your hands if you have an answer to that. What's wrong? Yeah, can we get the guy in red who's right close to the microphone there? Stand up. Give me your name. Stand up. Shout it out to the crowd.
Peter.
Yep.
And if everyone chooses 100,
It would be 67.
All right, good. So even if everyone in the room didn't choose randomly, but they all chose 100, a very unlikely circumstance. But even if everyone chose 100, the highest the average could, sorry, the highest 2/3 of the average could possibly be is 66 and 2/3. Hence, 67 would be a pretty good choice in that case. So numbers bigger than 67 seem pretty crazy choices, but crazy isn't the word I'm looking for here. What can we say about those choices, those strategies, 67 and bigger than 67, 68 and above? What can we say about those choices? Actually, there's somebody right behind you, the woman right behind you. Shout it out.
They have no payoffs for the
They have no payoffs? What's the jargon here? Let's use our jargon. Somebody shout it out. What's the jargon about that? They're dominated, all right? So these strategies are dominated. Actually, they're only weakly dominated, but that's okay. They're certainly dominated. Right? In particular, a strategy like 80 is dominated by choosing 67. Right? You will always get a payoff from choosing 67, at least as high and sometimes higher than the payoff you would have got had you chosen 80, no matter what else happened in the room. So these strategies are dominated. We know from the very first lesson of the class last time that no one should choose these strategies. They're dominated strategies. All right? So did anyone choose strategies bigger than 67? Okay, I'm not going to read out names here, but turns out 4 of you did. I'm not going to make you wave it, okay? All right? So, okay, for the 4 of you did, never mind, but, well, yeah, mind, actually, yeah. All right. All right. So once we've eliminated the possibility that anyone in the room is going to choose a strategy bigger than 67, it's as if those numbers 68 through 100 are irrelevant. It's really as if the game is being played where the only choices available on the table are 1 through 67. Is that right? Is that right? We know no one's going to choose 68 and above, so we can just forget them. We can delete those strategies. And once we delete those strategies, all that's left are choices 1 through 67. All right? So can somebody help me out now? What can I conclude now I've concluded that the strategies 68 through 100 essentially don't exist or have been deleted? What can I conclude? Let me see if I can get a mic in here. So stand up and wait for the mic. And here comes the mic. Good. Shout out.
That all strategies 45 and above are thus also ruled out.
Good, good. So your name is?
Henry.
Okay, so Henry is saying, once we've figured out that no one should choose a strategy bigger than 67, then we can go another step and say, if those strategies never existed, then the same argument rules out, or a similar argument, rules out strategies bigger than 45. Let's be careful here. The strategies that are less than 67, but bigger than 45, these strategies are not dominated strategies in the original game. In particular, we just argued that if everyone in the room chose 100, then 67 would be a winning strategy. So it's not the case that the strategies between 45 and 67 are dominated strategies, but it is the case that they're dominated once we delete the dominated strategies, once we delete 67 and above. All right? So these strategies, let's be careful here with the word weakly here, these strategies are not weakly dominated in the original game, but they are dominated. They're weakly dominated once we delete 68 through 100. So all the strategies 45 through 67 are gone now. So okay, let's have a look. Did anyone choose? Raise your hands. Be brave here. Did anyone choose a strategy between 45 and 67? Or between 46 and 67? No one's raising their hand, but I know some of you did because I got it in front of me, right? So at least 4 of you did, and I won't read out those names yet, but I might read them out next time. Okay, so four more people chose those strategies. All right? Now notice there's a different part of this. This argument, the argument that eliminates strategies 67 and above, or 68 upwards, that strategy just involves the first lesson of last time. Do not choose a dominated strategy. Admittedly weak here, but still. All right? But the second slice, strategies 45 through 67, getting rid of those strategies involves a little bit more. You've got to put yourself in the shoes of your fellow classmen and figure out they're not going to choose 67 and above. And so the first argument, that's a straightforward argument. The second argument says I put myself in other people's shoes, I realize they're not going to play a dominated strategy, and therefore, having realized they're not going to play a dominated strategy, I shouldn't play a strategy between 45 and 67. So this argument is an in-shoes argument. Now what? Where can we go now? Yes, so let's have the guy in the beard, but let the mic get to him. All right, and yell out your name.
Carter, you just repeat the same reasoning again and again, and you eventually get down to 1.
All right, well, we'll do that, but let's go one step at a time. So now we've ruled out the possibility that anyone's going to choose a strategy 68 and above because they're weakly dominated, and we've ruled out the possibility that anyone's going to choose a strategy between 46 and 67 because those strategies are dominated once we've ruled out the dominated strategies. So we know no one's choosing any strategies above 45. It's as if the numbers 46 and above don't exist. So we know that the highest anyone could ever choose is 45, and 2/3 of 45 is roughly, someone help me out here, 30, right? Roughly 30. All right? So we know that all the numbers between 45 and 30, these strategies were not dominated, and they weren't dominated even after deleting the dominated strategies. But they are dominated once we deleted not just the dominated strategies, but also the strategies that were dominated once we deleted the dominated strategies. All right? I'm not going to try and write that, but you should try and write it in your notes. All right? So without writing that argument down in detail, notice that we can rule out the strategies 30 through 45 not by just examining our own payoffs, not just by putting ourselves in other people's shoes and realizing they're not going to choose a dominated strategy, but by putting ourselves in other people's shoes while they are putting themselves in someone else's shoes and figuring out what they're going to do. All right? So this is an in-shoes, be careful where we are here, this is an in-shoes argument. At which point you might want to invent the sock. All right? Now, where's this going? So we were told where it's going. We were able to rule out 68 and above, then we were able to rule out 46 and above, now we're able to rule out 31 and above. All right? By the next slice down, we'll be able to eliminate, about 20 and above. All right, so 30 down to above 20, and this will be an in-shoes. Right? These strategies aren't dominated, nor are they dominated once we delete the dominated strategies. Nor are we dominated the strategies that are dominated once we delete the dominated strategies, but they are dominated once we delete the strategies that are dominated in the next. You get what I'm doing, okay? All right? So where does this argument going to go? Where's this argument going to go? It's going to go all the way down to 1. It's going to go all the way down to 1. We could repeat this argument all the way down to 1. Notice that once we've deleted the dominated strategies, I said before about 4 people chose this strategy. And in here, about 4 people chose this strategy. But in this range 30 through 45, I had lots of people. Lots. How many of you chose a number between 30 and 45? Right? Well, more than that. I can guarantee you more than that chose numbers between 30 and 45. All right? In fact, the people who chose, well, we started off, 33 chose in that range. And a lot more of you chose numbers between 20 and 30. So we're really getting into the meat of the distribution here, and we're seeing that these are choices that perhaps are ruled out by this kind of reasoning. All right. Now, I'm still not going to quite reveal yet who won. I want to take this just one step more abstract. All right? So I want to just discuss this a little bit more. I want to discuss the consequence of rationality in playing games. Slightly philosophical for a few minutes. All right? So I claim that if you are a rational player, by which I mean somebody who's trying to maximize their payoffs by their play of the game, that simply being rational just being a rational player rules out playing these dominated strategies. All right, so the 4 of you who chose numbers bigger than 67, whose names I'm not going to read out, maybe they were making a mistake. All right? However, the next slice down requires more than just rationality. What else does it require? Yes, okay, can I get this guy again? Sorry. Shout out your name again, I've forgotten it.
Nick.
Shout it out.
Nick.
Yep.
The assumption that your opponents are being rational as well.
Good, good. So to rule out the second slice, I need to be rational myself, and I need to know that others are rational. All right, that's illegible, but never mind. What it says is rational and knowledge that other people are rational. Now, how about the next slice after that? Well, now I need to be rational. I need to know that other people are rational. And I need to know that other people know that other people are rational. All right, so to get this slice, let's get this next slice here, I need rationality. As some of you know, that's widely criticized in the social sciences these days. Are we right to assume that people are rational? But to get this slice, I need rationality. I need knowledge of rationality. Let's call that KR. And I need knowledge of rationality. All right? And as I go down further, I'm going to need rationality. I need to know people are rational. I need to know that people know that people are rational. And I need to know that people know that people know that people are rational. All right? Now let's just make this more concrete for you. These people, the 4 people who chose this, they made a mistake. What about the 4 people who chose numbers between 45 and 67? What can we conclude about those people? The people who chose between 45 and 67. Shall I read out their names? No, perhaps I better not. What can we conclude about those people? Yeah, we're never going to get the mic in. Let's try and get the mic in there. Come forward as far as you can and then really shout. Yep.
They think their classmates are pretty dumb.
Right, right. It's not necessarily that the 4 people who chose between 46 and 67 are themselves thick. It's that they think the rest of you are thick. All right? And down here, this doesn't require people to be thick or to think the rest of you are thick. They're just people who think that you think, they're just people who think that you think that they're thick. All right, and so on. Now to get all the way to 1, we're going to need very, very many rounds of knowledge of rationality. Does anyone know what we call it if we assume an infinite sequence of I know, that you know, that I know, that you know, that I know, that you know, that I know, that you know something? What's the expression for that? Technical, believe it or not, technical expression. Technical expression for that in philosophy is common knowledge. Common knowledge. Which I can never spell, so I'm going to wing it. All right? Common knowledge. Common knowledge is I know something, you know it, you know that I know it, I know that you know it, I know that you know that I know it, etc., etc., etc. An infinite sequence. All right? All right, but if we had common knowledge of rationality in this class, then the optimal choice would have been 1. How many of you chose 1? Look around the room. Let's pan the room. So keep your hands up a second. How many of you chose 1? So actually, a lot of you chose 1. 1 was the modal answer in this class. A lot of you chose 1. All right? So those people did pretty well. They must have done, they must be thinking they're about to win. But they didn't win. So it turns out that the average in this class, the average choice, was about 13 1/3, which means 2/3 of the average was 9. 2/3 of the average was 9. And some of you chose 9, so if you're here, stand up. The following people chose 9. That's not right. Where are the people who chose 9? I've got them here somewhere. Sorry, there's only pages of people. Here we go. The following people chose 9, so stand up if you're here. And if you're that person's roommate if they're not here. All right, so Li Xing Chang, is Li Xing Chang here? Stand up if you're here. And Christopher Barrero, you can stand up if you're here. And William Fischel, are you here? Don't know if he's here. Jed Gleckstein, are you here? Jed Gleckstein, stand up if you're here. And Jeffrey Green, stand up if you're here. And Alison Hoyt. Stand up over here. No Alison Hoyt? Okay. And there's John Robinson. John Robinson? All right, so these people, well, can we get stay up a second so the camera can see you? There you go. There you go, all the way around, all the way around. Wave to mum at home. All right. Can we get a round of applause for our winners? So Jed has trustworthily brought back the $5. I'll go to focus for a second just to get it. Here is the $5. We're going to tear this into 9 pieces, except I get arrested and deported if I do that. So we're going to find a way to break this into change later, okay? And come and claim it afterwards. All right, but you're all entitled to whatever that fraction of $5 is. All right. Okay, so why was it, after all that work, why was it that 1 wasn't the winning answer? Why wasn't 1 the winning answer? Let's have someone we haven't had before. Can we get a mic way in the back there? Can we get a mic in there on the row you're on? See if you can point. Actually, yeah, good. Stand up, shout. Stand up, shout. Yeah, go. Shout away.
1 would have been the winning answer.
Louder.
1 would have been the winning answer had everyone assumed that the average would have been constantly compounded down to 1. But since a couple of people chose not incorrect answers, but the higher averages, then it was pushed up to 13.
So to get all the way, good. So to get all the way, thank you. So to get all the way to 1, we need a lot, right? We need not just that you're all rational players, not just you know each other's rational, but you know everyone else is rational. I mean, I know you all know each other because you've been at Yale, but you also know each other well enough to know that not everyone in the room is rational, and you're pretty sure that not everyone knows that you're rational, and so on and so forth, right? So it's asking a lot to get to 1 here, and in fact, we didn't get to 1. In fact, in previous years, we were even higher. So this was a low this year. In 2003, the average was 18.5, and in 2004 it was 21.5, and in 2005 we had a class that didn't trust each other at all, I guess, because the average was 23. All right, and this year it was 13.33. Okay, we're getting better there, I think. All right. One nice thing, by the way, this is just chance, I think. The median answer in the class was 9, which is spot on. So the median hit this bang on. All right. Now, what I want you to do is I want you all to play again. We haven't got time to do this properly, even though I've given you the sheet. So write down, don't talk to your neighbors, write down a number. Don't talk among yourselves, that's cheating. Write down a number. If you haven't got a sheet in front of you, just write it on your notepad. Write down a number. Has everyone written down a number? All right, I'm going to do a show of hands now. How many, right, we'll get the camera on you. How many of you chose a number higher than 67? Oh, this is spoil makers. Okay. How many of you chose a number higher than 20? How many of you chose a number higher than 10? How many chose a number between 5 and 10? How many of you chose a number between 1 and 5? How many of you, excluding the people who chose 1 last time, how many of you chose a number that was lower than the number you chose last time? Now keep your hands up a second. All right. So almost all of you came down. Why? Why are we seeing this massive contraction? I'm guessing the average number in the class now is probably about 3 or 4, maybe even lower. All right. Why are we seeing this massive contraction in the numbers being chosen? The woman in green, I forgot your name, I'm sorry.
We're not being rational if we pick a high number.
All right. So part of it is you yourselves have figured out, some of you, that you shouldn't choose a high number. Right? What else, though? What else? What else is going on here? Let's get somebody. There's a guy waving an arm out there. Yeah. You want to stand up behind the hat there? Yeah. That's you. Yeah.
Because we've repeated the game.
It's true we've repeated it. But what is it about repeating it? What is it about talking about this game that makes a difference? Let me hazard a guess here. I think what makes a difference is not only do you yourselves know better how to play this game now, but you also know that everybody around you knows better how to play the game. Discussing this game raised not just each person's sophistication, but it raised what you know about other people's sophistication. And you know that other people now know that you understand how to play the game. So the main lesson I want you to get from this is that not only does it matter that you need to put yourself in other people's shoes and think about what their payoffs are, you also need to put yourself into other people's shoes and think about how sophisticated are they at playing games. And you need to think about how sophisticated do they think you are at playing games. And you need to think about how sophisticated do they think that you think that they are at playing games, and so on. Right? This level of knowledge, these layers of knowledge lead to very different play in the game. And to make this more concrete, if a firm is competing against a competitor, it can be pretty sure that that competitor is a pretty sophisticated game player and knows that the firm is itself. If a firm is competing against a customer, let's say for a non-prime loan, perhaps that assumption is not quite so safe. It matters in how we take game theory to the real world, and we're going to see more of this as the term progresses. Now, I've got 5 minutes. Do I have 5 minutes left? So I've got 5 minutes to just take a little small aside here. We've been talking about knowledge and about common knowledge. Now, I just want to do a very quick experiment. So everyone stay in their seat. I'm going to get 2 TAs up here. I want to get Ale and Kai up here. And I wanted to show that common knowledge is not such an obvious a concept as I've made it seem on the board. Come up on stage a second. You can leave the mic, it's okay. All right, here we have 2 of our TAs. Actually, these are 2 head TAs. And I want you to face forward so you don't see what I'm doing a second, okay? All right, I'm about to put on their heads a hat. All right? All right, here's a hat on Ale's head. And here's a hat on Kai's head. Let's move them this way so they're in focus. All right? Now, you can all see these hats, and they can see that. And if they turn around to each other, they can see each other's hat. All right? Now, I want to ask you the question here. Here is a fact. All right? So, is it common knowledge? Is it common knowledge that that at least one of these people has a pink hat on their head? Is it common knowledge? So I claim it's not common knowledge. What is known here? Well, I'll reveal the fact to you now that in fact Ale knows that Kai has a pink hat on his head. So it's true that Ale knows that at least one person in the room has a pink hat on their head. And it's true that Kai knows that Ale has a pink hat on his head. They both look absurd, but never mind. But notice that Ale doesn't know the color of the hat on his own head. Right? So even though both people know, even though it is mutual knowledge that there's at least one pink hat in the room, Ale doesn't know what Kai is seeing. So Ale does not know that Kai knows that there's a pink hat in the room. In fact, from Ale's point of view, this could be a blue hat. So again, they both know that someone in the room has a pink hat on their head. It is mutual knowledge that there's a pink hat in the room. But Ale does not know that Kai knows that he's wearing a pink hat. And Kai does not know that Ale knows that Kai is wearing a pink hat. Each of their own hats might be blue. So notice that common knowledge, thanks guys, common knowledge is a rather subtle thing, thank you. Right? Common knowledge is a subtle thing. Mutual knowledge doesn't imply common knowledge. Common knowledge is a statement about not what I know, it's about what do I know the other person knows that I know that the other person, and so on and so forth. And even in this simple example, where you might think it's obviously common knowledge, it wasn't common knowledge that there was a pink hat in the room. Does anybody have smaller siblings or children of their own? They can have a pink hat at the end of the class. All right, we'll see you on Wednesday.